In today's lecture, I'll introduce the idea of the ideal experiment. This idea was proposed by Ken Burnham and provides a nice way of understanding some of the issues we face when conducting experiments in the real world. In this example, we get to play God. And by playing God, what we mean is that we can apply a treatment to every individual in the population, record the response of that experimental unit at some time t later, and we might record that outcome as xi1, I being the ith individual, 1 being treatment 1. Reset the universe to time 0, in other words, we need a time machine. Assign treatment 2 to all units in the population, and again, record the outcome. And we can repeat that through all of the V different treatments that we might be interested in. All right, so let's start off with the ideal experiment 2.0. This is what Ken Burnham refers to as a thought experiment. And say we're interested in looking at the effects of vitamin C on the number of colds that people get over time. And you might be aware of this, that there was a famous scientist by the name of Linnaeus Pauling who actually did a study on this, published something about it. He was I believe he was a molecular biologist back in his day, but he dabbled in some other areas as well. And he was interested in whether vitamin C might have an influence on colds and general health. And Ken Burnham talks about the outcome of that experiment that he did, and also a pretty major fatal flaw associated with that experiment. So despite being a Nobel laureate, Linus Pauling is able to make mistakes as well. So you might be interested in listening to the full interview I did of Ken, where he talks about what happened with that experiment and why there was a problem with it. Anyway, getting back to our ideal experiment 2.0, say we're interested in looking at various levels of vitamin C and how that might affect the number of colds that people get. So V would refer to the number different treatments that you're applying, from no vitamin C up to 10,000 milligrams a day, and a number of values in between if you're interested. Our population, since we can play God, we can essentially treat the entire population in the US, for instance, in this case, and our God can just infuse everyone each day with the proper amount of vitamin C, so we can do our experiment. The outcome would be the number of colds that each person has in a year, and that's described as a vector, C sub I, where I is the identity of the individual, from 1 to 330 million. And another thing to consider are the environmental factors that could impact the outcome of this experiment. Now, for our particular time frame that we're looking at, there will be no confounding environmental effects because we're using a time machine. So we apply the treatment to all the individuals in the US, let it run through a year, count all the colds, reset the time back to the initial condition, give them all a different dosage of vitamin C, run it through. So in terms of those environmental factors confounding the output of this particular experiment, there's no problem. But you could say, well, the year that you chose to do this was a warmer, drier year. And so that's why you didn't find much of an effect. For instance, if you did a 2015 that was known to be cold and rainy, then you would have found a big effect. So there's another part of the environmental factor here that you could consider, and of course, being a God, perhaps you could run this across many different years and look at how the outcome varies depending on the type of year it is and so on. But in terms of our outcome from this particular experiment, we're able to control all that, so we don't have to worry about it. This is really great because we don't need to randomize. We're using the entire population and all of our initial conditions are identical. The external time-related factors are also identical because we've got a time machine to reset things, so we don't have to worry about year-to-year variation in environmental factors. And it's very easy to calculate our treatment effect. We just take the difference between number of colds that someone obtained under the first treatment versus number of colds under the second treatment, and that difference is exactly the treatment effect. And so in this case, if treatment 1 is a control, not taking any vitamin C supplements, all of our comparisons are 1 versus 2, 3, 4, however many different levels of vitamin C we decide to include in our experiment. So just to reiterate, by resetting the universe to the initial conditions each time we apply a new treatment, we are using each experimental unit as its own control. So we are doing exactly the idea of seeing how the ith unit, in this case person, will respond under identical conditions over the chosen time interval for all treatments. So we measure effect size exactly. There's no experimental error. And by experimental error, we refer to the failure of two identically treated experimental units to yield identical results. So in most experiments, not every experimental unit is going to respond to the treatment exactly, and therefore that variation can sometimes preclude our ability to see an effect. In this case, we don't have to worry about it because we're using the same individual through the same time period. The really nice thing about this ideal experiment is no inferential statistics are needed. We know the exact response of every unit to the population in the population under the exact same environmental circumstances for all of the different treatments. So like I mentioned before, to compare any two treatments, we just calculate the differences between our control and any one of our other treatments and tabulate the summary values. Now there still are some questions that you'd have to address. One is, how many different treatment levels do you want to apply? Do you want to have 5 different levels from 0 to 1,000 milligrams? Do you want to have 100 different levels from 0 to 10,000 milligrams? So there's really an infinity of possible treatments, so you need to decide which ones you want to examine. And depending on that, your outcome vector C would have an infinite dimension depending on both how many different treatments you want to apply and whether you want to consider different years, for instance, where the environmental effects might be different. So in one year, it might be generally warmer and drier across the United States, and so you may have less of an impact of vitamin C on number of colds than in another year when it tends to be wetter and colder more of the time. So really, even though we have talked about um, excluding all environmental effects, if there were some big differences from year to year, you might want to consider whether that has an impact. The key point, though, is that in this case, we're using each experimental unit as its own control, and in that way, we can't get any of the outside stochastic or other deterministic kind of effects that could somehow lead us to questioning our conclusions. And we should really judge real experiments against this ideal control treatment comparison. Now we'll look at a situation where we can't sample the entire population. We'll refer to this as the ideal experiment version 1.0. So assume now that Iea goes to Zeus and he says, you know, our budget is a little bit tight this year. I don't have enough to give you the ability to sample all of the units of the population, so you're just going to have to take a random sample. So then EA is going to have to go and figure out a way of randomly sampling all of the individuals in the population of the United States. Again, she's a god. Maybe that's not much of a problem. She still has use of the time machine, so she can reset things now to time 0. And because we're not sampling every individual in the population, we need to make an inference from the sample that we draw to the total population. There could be potential differences between the sample and the entire population, and so we're going to have to use inferential statistics in order to make that leap from the sample to the population as a whole. And we'll talk about some of the issues associated with that when we talk about sampling. So that brings us to reality. We don't have a God that can help us with this experiment, which is where we all start. And so we don't have a time machine. We can't sample the entire population. So we're going to have to compare different samples of individuals from that population, some of which get 0, 100, 1,000, whatever our different treatments are of vitamin C. Of course, those must be a random and representative sample from our target population, which is often very difficult. Think about doing this across the entire US, for instance. Oftentimes for these kinds of medical studies, they're just done with students from the university where the test is being conducted. And that obviously limits the inference that you can make to the entire US population. And of course, the key thing, as we talked about, is you can't use individuals as their own control. And so the effect of the treatment is measured by measurement error. Do people really remember how many colds they had, or are you measuring that precisely enough? There's now experimental error, as we talked about. No 2 experimental units. In this case, people are going to respond in the same way to the treatments. Some may inherently have a less powerful immune system and therefore get more colds than somebody else, even with the same amount of vitamin C. And there could be confounding effects. So some people may inherently just be more prone to washing their hands and following methods of hygiene that will reduce their chances of picking up viruses and getting colds. Others might live in more rainy or cold environments where conditions are more conducive to picking up a cold and so on. So all of these things have to be considered when we're talking about real experiments that we are doing. I want to just finish up with a quick overview of some of the concepts that you'll be covering in the readings, just to help with the assignments that you'll be doing. In terms of approaches to conducting science, there's 3 general categories that are usually reviewed. One is induction, forming general conclusions based on multiple observations, often referred to as going from the specific to the general. Second is deduction, deriving a conclusion using a general or universal premise and a set of facts that you have at your disposal. And third is what Romsberg refers to as retroduction, and term that's not used much in the literature. And it consists of developing an explanation or a hypothesis that best explains a particular set of observations. And because the conclusion or the hypothesis is developed after looking at the data, it's sometimes given the term storytelling, which is obviously not a complimentary description. And there's a really nice review of these different approaches in table 1.1 of the book. So just a quick example of these different types of approaches and how they might be applied in a particular situation. Induction is classic, again, from the specific to the general. So if we go out and look at 1,000 swans and we see that everyone that we observe is white, our conclusion is that all swans are white. So we're going from the specifics of the observations to the general conclusion. Deduction applied to this same sort of question might be that you are a geneticist and you've identified 20 genes in the bird genome that code for pigment color in feathers. And you look at the genome of swans and they don't possess any of those genes, or they're all turned off. Therefore, you would conclude, based on your general premise that these genes code for color, that swans would have white feathers. Retroduction would be, again, going storytelling about a set of observations. So you go out and you observe that all swans are white. You're wondering why this might be the case. And you say, well, swans are big birds and therefore they have fewer predators. And because of that, they can be very conspicuous in white and not be at risk of predation. So you might make the conclusion that all large birds or even large animals might be white because predation is not an issue in there for them. Of course, we all know that ahead of time that's not true, but this is an example of how that kind of hypothesis might be generated from a particular set of observations. And again, just a quick review of the hypothetico deductive method. It's usually shown as a process, like shown here in the figure, where you start with a hypothesis, you derive predictions from that hypothesis, design an experiment to test those predictions, go out and conduct it, run your tests or look at the outcome of that experiment, either accept or reject your hypothesis based on the outcome of that statistical test, and then that feeds back into either revising your hypothesis and moving forward, or as Popper would point out, accepting your hypothesis or failing to reject your hypothesis doesn't mean that that hypothesis is correct. There may be more stringent kinds of experiments that you could do or different predictions you could come up with to, again, try to really, the whole approach here is to tear down that hypothesis to show that it's false, because that is really the only way that we make progress scientifically. And again, just a quick overview of the paper that I have you reading this week, Strong Inference by Platt. He gets into a lot of examples, albeit very old examples of molecular biology and physics and so on. Don't want you to get too bogged down in that. A lot of that is way in the past now. But I think the key things that Platt put forward in his paper about strong inference is, first of all, starting with multiple working hypotheses. Secondly, devising crucial experiments with different outcomes for each hypothesis that you can use to test the predictions of those hypotheses. Conduct the experiment to get a clean result, and that often is more difficult than it might seem. Re-examine the hypotheses and then repeat. And he refers to it as kind of a example of climbing the limbs of a tree, and there's one limb branch that's going to be the right answer to the question that you're addressing, and what you want to do is try to choose which of those branches to take in order to lead you to the correct result. There's been some criticism of Platt's paper and how he puts some sciences in the good category and others in the bad category. And there's a little bit of discussion of that in your textbook. But I think one of the really important points that come out of Platt's paper is this idea that it's always best to have multiple hypotheses when addressing a question rather than latching on to one favorite hypothesis. And this is what often gets us into trouble in science, is that we think, well, I've come forward with this hypothesis about, the factors that influence the number of ducks that might be in the population next year. And that's my favorite hypothesis. And I'm going to do everything I can to defend that hypothesis from anyone else who might want to criticize it. Now you're really moving out of the realm of science and into, a situation where you're using your own biases to color the outcome of the results of potential studies and so on. And by using multiple alternative hypotheses, that gets us away from this personal involvement in our particular hypotheses and to the place where we want to be, where we're truly looking at each different hypothesis in a very objective manner. And again, just a quick overview of what's expected this week, and I'm not going to be able to do this in every lecture. Readings, the reading by Popper, again, this is a fairly old paper written in a much different form than you see in scientific writing these days. Only sections 1 and 2 are required. It can get very long if you try to read the whole thing. And then there's the sections in the textbook, again, reading for the key points that have been illustrated in this lecture. Obviously the ideal experiment lecture, which you've just finished now, and then 2 assignments to complete the induction, deduction, retroduction assignment, and then to participate in the discussion on the scientific method.